Hello, it's Keith here, and this is lesson 1 of the simple series of my SH2 assembly programming tutorials, the Super H. Now we're looking at the Saturn today, and in the simple series we create, very much like the Hello World series, a single ASM file that does a single job. Now the idea is it's easy to port if you're not using the same assembler as me, and of course if it's a single file it's easier for you to learn from. Now today's example is a bit of a combination. What we're doing is we're showing a sprite to the screen, and we're moving that sprite around the screen with the joypad. So I'm using the cursor keys here on this emulator, but it's the joypad I'm using really. So this is what we're going to be looking at today. We're going to look at how to get the screen on, how to get a bitmap on the screen, and then how to read in the joypad, and then there's some example code moving it around the screen. So a nice simple example to get you started. So let's go over to the source code, let's take a peek at it. Okay, so this is the file we're looking at today. This is sat.joy Sprite, that is the example file for today. Now we're going to go through it quickly. If you want more instructions on how to assemble a file and the sort of very basic structure, please see the Hello World series. I covered the assembler and the emulator, how to start the emulator in that one. I'm not covering that here, but we're going to go over the basics anyway. Now we're generating a binary file, so we're not generating a CD, we're generating a bin file our emulator can execute. The starting address that needs to be at is 6004000. So that's the start of our code. And then the first thing we're doing is we're setting up the screen. So we're using VDP-2, the bitmap screen there, and this is the base of that hardware's registers. We've got to set various things up. We're setting up the screen layout here and the memory mapping, so that's what we're doing there. The screen we're using is a 1 byte per pixel, so 256 color screen. A nice easy screen to work with, and it's rather strangely 512 units wide in memory but only 320 units wide on the screen. So I guess it's got a scrolling ability. It certainly does. We've got scrolling options here, so that's a good clue. But as I say, you'll see later on 512 mentioned when we're moving down the line. Screen's only 320 pixels visible though, so we'll see that as well. Okay, so after setting up the screen, we're setting up the scrolling positions. These we're just setting up with some defaults here. We're not using any scrolling in today's example. And then we're doing some more setup of the screen here. We're defining the map size here and selecting the color format, I guess, here. So that is setting that up. And then what we're doing here is we're turning on the layer and we're enabling the screen here. So these are just turning on the screen, and this is sort of this is the sort of most basic screen you can have. These are tutorials, we're only going to cover the basics. I'm not going to go into anything like 3D. I mean, really, I'm an 8-bit programmer, so these 32-bit systems are way outside of what I ever plan to do. So I only ever do bitmap stuff in them. Anyway, so we've got our bitmap screen on here. The next thing we're doing is defining the colors. We need some colors, otherwise we won't see anything. So the color memory is at that address. We've got our palette defined here, and each palette entry is defined by 2 bytes, one 16-bit word. Now the palette entries are down here. So these are the palette entries. So that one is black, you can see there, and you can see them all here. And they're in blue, green, red format, 5 bits for each channel. Very nice and easy. Now while we're down here, we'll have a look at the other things we've got. We've got an LT-org. If you don't know what that is, please see my Super H tutorials, because you need to know that. LT-org is when we try and define an entry in our code that is too long to exist within the code itself. For example, that apparently immediate value there is actually stored as a literal at the LT-org. So we need to have that, and we need it to be aligned. So that's what that is. There's our palette. We're realigning here to make sure we're properly aligned. We're defining some memory called in user RAM. Now this ROM file is actually copied into RAM before it's executed, so we'll actually be running from RAM and not a CD or ROM or anything. But so that's some memory, and I've got some comments there. It's possible uses here. So player X and Y we're going to use for our player's cursor position. You'll see that in our code later on. And then finally here, we've got this bitmap being included with binclude. Now this is a binary file. This was exported with my Sprite editor. It's my free and open source editor that's included in my DevTools kit. And this can output in various formats. And the one we're actually using today is the same as the format for MS-DOS VGA, 1 byte per pixel. So very straightforward there. So that's our source file, and that's what we're going to be showing. Now, so we've turned our palette on here, and then what we're going to do is we've got the code here that is our sort of game, if you can call it that. Not really a game, but it's where our game would be, and it's our test code in this case. We're going to look at the test code later on. What we're going to do first is we're going to discuss the routines that code relies on to actually get the work done. Now the first one we're going to look at is the show sprite routine. Now this show sprite routine is past a width and a height of the sprite to show. It actually loads in the X and Y position from memory here, so it's not past those in the format it currently stands. Now when we want to calculate the pixel position to start drawing our sprite, what we're going to do is we're going to take the memory, the VRAM base here at 25E and then 5 zeros there. That's the start, that's the top left pixel if you will. We're then going to add the X position in pixels because of course 1 byte per pixel, so we just add the X position, that's moved us across, and then we need to move down, and so we need to multiply the Y line that we want by the width of the logical screen, not the visible one. Remember the visible one's 320 pixels, but the logical one is 512 bytes. So we're multiplying by 512 here using Mulu, multiplying the Y position by 512, loading in the low part of that because Mulu doesn't change the register, it stores it in the special MAC-H and MAC-L registers, so we're loading MAC-L there. And we're adding that to our VRAM base. Now, the long and short of it is once we've run these lines here, we have R12 containing the VRAM destination, the screen position in VRAM. Now, the show sprite routine is going to show the sprite R13. We load the address of the sprite bitmap in R13 before we execute this. And we've, of course, calculated from the X and Y position in memory. And we need to specify the width and height in R10 and R11. Now, when it comes to drawing our sprite to the screen, it's we're going to work one block at a time. We're working in 32-bit longs, so we're effectively doing 4 pixels at a time. But the procedure is going to be the same each time. Now we're going to need to move down one line 512 bytes. Yeah, remember the logical screen is 512 bytes. And so what we're doing here, we're backing up the width of the screen and also the VRAM destination for convenience here at the start of this loop. And then what we're doing is we're moving a 32-bit value, 4 pixels, from our source bitmap in R13, and we're incrementing R13. Now what we're doing next is kind of optional. It's handy for my code here, but you may not want to do it. We are loading in the current memory from the VRAM into R4, and then we're XORing the current memory on the screen with the data we want to write to the screen, and then we're writing that back to the screen. R12 is the VRAM destination. So this is an XOR, and XOR is an inversion operation. Now why am I doing this? Well, if we draw the same object to the screen using XOR twice, then the second time we'll remove the first time. So that is a very easy way of removing sprites. If you've got lots of sprites going over the screen, it doesn't matter if they overlap. You XOR them and it removes them. So that's a very simple way of getting started with things. But if you're doing more complex games, especially on a very powerful system like the Saturn, you probably want to use a double screen buffer and things like that and redraw everything every time anyway. But for a simple example here, it's convenient to use the same code to remove a sprite as to draw it. So that's why I do XOR here. It's handy on the 8-bit systems, and so I've transferred it across here. Now we're moving 4 bytes to the screen, so after we've transferred the long, we're adding 4 to R12. Now we're using DT for at the end of our line, but we've actually transferred 3 extra bytes there. DT will subtract 1 from our X count, but we've transferred 4 bytes, so we're subtracting 3 here before we do that. Originally this code worked at the 1 byte at a time, but it worked fine for 32 bits, so I converted it, so we're moving 4 pixels each time here. So when we get down to here, we've done an entire line. What we then do is we restore the Y position here. We add R3. R3 contains the width of the logical screen, and then we decrement our height of our sprite, and we repeat until we've drawn our sprite to the screen. So that is the drawing routine, and as I say, because drawing twice will remove the sprite, it's also our removing screen. Very straightforward. Okay, so that's how we draw our sprite. How do we actually get in the current state of the controls? Well, we're going to use this getJoy routine here. Now, if you want to know the details of how this works, this uses the System Manager and Peripheral Control SMPC hardware, SMPC. Now, if you want to see this, there's a technical document that you can find. If you look on archive.org, you can get this. That is the name of it there, and you want to look at page 21 onwards, but you probably want to read the whole thing, to be honest. And that's what I've based this on. So what do we do? Well, this piece of hardware will basically read in the data for us. We need to set some things up first. So first of all, we're setting up the various ports. We are setting up DDR1, a data port. We need to set all of the ports to all the bits to in on this, and so we write the value with all the bits of 0 to that port there, and that will set them to input. If they were set to 1, they will be set to output, which isn't what we need here. Now then what we're doing is we are changing IO select 1 here. We want to set that to SMPC. If we set it to SH2 direct, we would have to do the actual data reading from the joystick ourselves. I tried, I couldn't get it working right. So if you can, great, you're cleverer than I am. Very, very possible. But I had to use the SMPC. I couldn't get direct working. So anyway, we write 0 to do that. And then the other one we're doing is we are disabling the VDP latch here. We don't want that. That's linking the controller to the VDP. I think that's maybe for light guns and things like that, but we don't want it here. Okay, so that's got our hardware ready to actually send the command. Now what we do next is we need to send a sequence of commands and data bytes to initialize the command that we want. Now the first thing we do is we set the busy flag here of that port there. These are all ports within the SMPC. These are all various registers. These ones are settings. That is the command port there. I'm not reading out these ridiculously long numbers. And that is the status. So we're setting the status as busy before we start. Now what we then do is we are going to basically set this value here. We're writing a value of 0 to that port there. Now this is basically specifying the data that we want. We just want the basics. If we put a 1 in, we actually get the current time and things, the current date and time. But I was actually getting some glitches with that. Maybe it was outputting too much data sometimes and overflowing. But that was causing some malfunctions for me. So I've got this set to 0, which is just the basics, which is the joystick controller. We need to set this here as well. So we are going to set the amount of data we want back here, I think this is. So we're setting that up. And then we need to write this value of F0 here. That's just a fixed value. These values I've gotten from that documentation. So this documentation will tell you the options and in some cases the fixed values. And so that's what I use to base this on. The final thing we need to do is the actual command number, and that is 10 in hexadecimal. That is known as int back, and that is interrupt back. That's what the command is called. And its more useful name is SMPC status acquisition. And so we're acquiring the status of the hardware, mainly the joypad. That's what we want. Okay, so that's what we've done then. Now we wrote a 1 to the status flag up here, and what we do now is we wait for the status to be ready. So we're reading in that status flag and waiting for it to become 0. Now when it becomes 0, the hardware has actually read the status and sent it back to us. So until then we're just waiting. It shouldn't take long, so just a few ticks probably. Okay, now when it comes back at memory address 2010020 onwards. So the ones up here, these lower numbers, those were the writable registers. These are the readable registers. It's important to note all of these are a single byte. Now, quite interestingly, each 16-bit word contains the same byte twice. So both the high and low byte within each word should contain the same value. So we're reading from various offsets here. To get our values. And so what we're going to get is we're going to get right, left, down, up, the fires A, B, C, and the start button. Those are the sort of old Genesis ones. And then we also get the X, Y, Z, and left and right triggers. Now, these are all contained in the various bytes that the hardware responds to. Now, it does actually respond with a few extra bytes. Now, the first byte it responds to is actually the multi-tap status, and the second byte it responds with is the pad type. Now, actually, most pads have standard pad functionality, and I'm being a little bit cheap, and I'm not checking that, which is probably very unprofessional, but this is a hobbyist tutorial, so I don't really care about that. So what I'm doing here is my multi-platform tutorials are from port code between systems, and so what I try and do is make everything work in the same way. So rather than the format that the hardware provides us, which is that, what I'm doing is I'm going to shift the bits in there into my standard format. Now the standard format from me is that the 16-bit value that this returns should have up, down, left and right in the lowest bits, and then the fires in sort of descending order. So the most important one should be first, and then second and third and fourth, and then any extra ones should be in the next byte. So what I'm doing here is I'm shifting the various bits around. So here I'm reading in the byte that contains right, left, down and up here. I'm then shifting those 4 bits to the right and masking those, and that gets up, down, left and right in the least significant bits here. Then I'm doing the fires, so I want A, B and C here and start here, so I'm shifting those left and masking those. And then finally I'm doing the same with the triggers here and the X, Y, Z, which I certainly don't need. Most of my tutorials are based on a single fire button or 2 because, as I say, I work in 8 bits most of the time. But anyway, this routine, the long and the short of it, this routine will get the joystick directions in a standard format, and we use that in our main loop. So we're back here, back in our main code just after we'd set up the palette here. And so we've got a main loop here, which is our infinite loop that it runs forever while our program is running. And before that infinite loop, what we're going to do is we're going to show the initial position of our character, our player character. So Chibico bitmap is our player mascot. Chibico is the mascot for my website. That's that character there. We don't need to see that advert again there. And so that's the bitmap we've got there. And we've got the width and the height here, 48 by 48 pixels. And we run the show sprite routine here to show it to the screen. Okay, so what we're going to do next is we're going to read in the joystick. That's what we're doing here. Now we don't care about fire buttons in this example, so we're masking out up, down, left and right here. And we're waiting until one of those is pressed. So what we're doing, these will go to 0 when a button is pressed down. So if they're 1, the button isn't pressed. And so we're going to just keep repeating the infinite loop until a button is pressed. Now once a button has been pressed, we're going to then decide what button was pressed, compare the current position of the player's sprite. We don't want to allow the player to go off the screen, and move the player if the player is pressing the fire button, pressing the direction button, and the player can move in that direction. Now throughout this routine, R1 is going to be the X position and R2 is going to be the Y position, and the getJoy has loaded the player directions into R0. So what we're going to do now is we're going to test each direction the player could be pressing. So first of all, we're going to test the up direction here, which is bit 0 here, and we're going to branch if that direction is not pressed down to joy not up. Now if that button is pressed though, what we're going to do is we're going to test the Y position of the player. Now the player's Y position is in R2 here, and so we're going to compare that to 0, 0 being the top of the screen. Now if the player's position on the Y axis is 0, then we're going to skip over the next command, because the next command would move the player up the screen, but if the player's already at the top of the screen, we don't want to do that. Otherwise all kinds of crazy things could happen. So that's what we're doing there. Now that's the up direction done, and then all we do is the exact same thing for down, left and right. So now we're testing the down direction. Our screen is 224 pixels tall and our sprite is 48 tall, so we are subtracting that because we're testing the top left of our sprite position here. And so if the player is at the bottom of the screen, we aren't moving, but if the player isn't at the bottom of the screen, we're moving down the screen by adding 1 to the Y position. We're then doing the X position, comparing to the far left of the screen and moving left if the player can move left, and the same for right. So now R1 and R2 are the new position of the player after the move. Okay, there's one last thing we want to do though. So what we're doing here is we're backing up the X and Y position here and restoring them here using the stack. And the final thing we're doing here is if we've decided the player needs to move, we're actually removing the old sprite here. We're using the old sprite position and removing the sprite from the screen, because remember, if we draw the sprite twice to the same position because of the XOR, we remove it the second time. Now we could have some fun here. If I remove this line here and I run again, well, you will see everything looks just fine and dandy, but then when I start moving around, we're drawing a big trail of nasty, messy chibicos, and the reason for that is we no longer have that removal routine, so the next draw is being done at a different position, and drawing at a different position doesn't remove the original. If we weren't using XOR, we would get a different effect. I can show you that too. If I go to the code down here, and if I change this XOR command here, and if I just remove that, and if I run this again, well now, we're kind of leaving trails, because basically we're making no attempt to remove the old sprite, but we are now drawing the sprite without the XOR over the top of whatever's already there, and so a couple of the edge pixels are leaving trails. So yeah, so you get different effects depending on the way you do it, but I find XOR is a nice easy way to get started. So that's removing the sprite, and then what we're doing here is we're updating in memory the new X and Y position from R1 and R2, and we're drawing the sprite to the screen again here. Now the last thing we've got here is very simple, very crude. We've got a simple delay loop. This is a really, really basic delay loop. We're just doing a count, and we are just repeating until that goes to 0, so you can make your code faster just by reducing the value there. Change that to FF. We'll be going around like crazy, far too fast, and it's not drawing properly. And if we want it slower, we can change that to larger. Now, the other option, of course, would be to wait for VBlank. So that would give us controlled timing, irrespective of how much was going on in our code. But for a simple example like this, I thought it was adequate to just use a crude loop. Anyway, that's all we've got today. If you've liked what you've seen, please like and subscribe. We're going to do another tutorial next time on the simple series of Super H. We're going to do the 32X, so if you liked what you've seen, please stick around for that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.